Welcome to Logic Bytes. In this video, we explore Section 1.4, Maximum Likelihood Estimation, or MLE. It's a fundamental technique used to estimate parameters from data. The likelihood function, written as L of theta, or its log version, tells us how likely a parameter value theta is, given the data we observed. The maximum likelihood estimator, or MLE, is the value of theta that makes the likelihood function as large as possible. Formally, it's the value of theta that maximizes L of theta. For one-dimensional or scalar theta, we often solve what's called the score function. That's the first derivative of the log likelihood function with respect to theta. We set this equal to 0 and solve. To confirm that we've found a maximum, we also check that the second derivative is negative. We also use the second derivative to measure how sensitive our estimate is. This gives us the observed information, which is minus the second derivative, of the log likelihood, evaluated at our MLE. We can also compute the expected information. That's just the average of the observed information over many hypothetical samples. And thanks to a key result in statistics, we know that as the sample size increases, the MLE becomes approximately normal. That means it follows a normal distribution centered at the true parameter, with variance equal to the inverse of the expected information. This result lets us build a confidence interval for our parameter. It's the MLE plus or minus a z-score, based on our chosen confidence level, times the square root of the inverse observed information. Sometimes the log likelihood isn't differentiable, like in the uniform distribution example from earlier courses. In those cases, plotting the log likelihood surface can really help.